Good morning, everyone. I'm Raaghini. So today I'll be presenting about sustainable carbon nanotube synthesis from recycled polypropylene. Okay, as we know in the introduction, plastic waste poses significant environmental challenges due to its non-degradability and limited recyclability. So, for example, there will be pollution like ocean pollution, water pollution, air pollution. So, because of this, the aquatic life will be endangered, and even the ozone depletion can be happen. So, our main purpose for this project is to transform plastic waste into valuable carbon nanotube via catalytic thermal decomposition. So this project will align with Sustainable Development Goals 12 SDG 12 on responsible consumption and production. So this is the molecular structure for polypropylene. And our main purpose is to transform the plastic waste into a valuable carbon nanotube. Okay, as we seen in this picture, the plastic waste such as bottles or food container, it will go through the catalytic conversion, which contain temperature, reaction time, and catalyst, and it will be transformed to carbon nanotube or graphene. So carbon nanotube, it will consist of composite catalyst support and structural materials, and also electronics. So these are the one of the applications. Next, for problem statement. As we know, in this pie chart, the 76% of plastics are improperly disposed and only 24% of plastic are recycled. So the improperly disposed plastic will cause ocean pollution and even landfill overflow. So the 24% of recycled plastic waste only we will be using to transform to carbon nanotube. So for the methodology, as we know in this picture, we need to prepare food container and ferrocene, like prepare 3 separate boards, such as in this picture, and 10 gram of recycled polypropylene and also 10 gram of ferrocene catalyst are prepared. Step 2.
This shows the CVD reactor setup. Next, the boards need to be placed inside the ceramic tube. Then open the system and adjust the pressure. Next, adjust and tighten the flange bolts to ensure there is no leakage of argon gas. Ensure the bubbles form in the beaker. Next, turn on the system and set the temperature.
Last step, we need to have the characterization. So the produced CNTs will be analyzed using SEM, XRD, and Raman spectroscopy. So for the result and discussion, after we produce the CNTs will be formed like this in powdered form, which is in black color. So the picture shows before CVD and after CVD. Next, from the CNTs, we will be test the characterization. The first one is structural analysis of CNTs. So as we see in this XRD graph, the peak around 2 theta is equals to 25 degree marked in red, tells us that carbon CNTs were formed at all temperatures. This means our synthesis process successfully created CNTs. So the peak is sharpest at 900 degrees Celsius, which means the CNTs are more ordered and have fewer defects. This is called high crystallinity. And at 700 degrees Celsius, the peak is broader, meaning the structure has more defects and lower crystallinity. Next, for the SEM, as we see in these images, that's ABCDE. So the CNT growth is highly dependent on temperature. So at 600 degrees, the process is incomplete. It will lead to poor CNT formation and a lot of amorphous, like disordered carbon. So between 700 to 800, the CNTs start to form properly and group into bundle with fewer impurities. And at 900 degrees Celsius, we get the best quality of CNTs, well formed and high structural order. So, however, at 1000 degrees Celsius, the structure becomes disordered again as we see more amorphous carbon, which is not ideal CNTs. Next, for the Raman analysis of CNTs, the lower ID over IG ratio means fewer defects. So the ratio drop from 1.343, which is 700 degree, to 0.65, which is 900 degrees Celsius, showing improved structural order. So at 900 degrees Celsius, it produced the best CNTs. So the G band, which is the graphitic order, it is the strongest, confirming the highest crystallinity. And too high temperature causes defects as well. At 1000 degrees Celsius, the ID over IG ratio it will increase to 0.75. So next, for the novelty, the sustainable approach to waste management by converting plastic waste into nanomaterial, and it has high purity and high crystallinity as well. For the advantages, it has eco-friendly, so it can reduce plastic waste and accumulation, and also cost effective. It can utilize waste material for nanomaterial production. For the commercialization, we can get sensors, automotive parts. For the conclusion, high quality CNTs can be produced sustainably using ferrocene catalysts to break down recycled PP thermally. This study identified 900 degrees Celsius as the optimal synthesis temperature, yielding CNTs with highest carbon output, best morphology, and minimal defects verified through Raman spectroscopy, XRD, and SCM analysis.